Got it. Anyway, I'm Marty Lynham, WA7MJL, and I'm talking this afternoon about section T3, propagation. Let me share my screen here. And I'm not moving. Probably shared the wrong one. Just 1 second here. Okay, sub-element T3, radio wave propagation. This is a fairly complex one for technicians, but as you advance through your licenses in amateur radio, this is probably one of the most important sections that you'll see. Hams that live in the HF world live and die by this one. Anyway, if you've got any questions, you can email me at mjlynham@live.com, and I'll be more than happy to answer any questions that you might have. So let's get started on this. T3A, radio wave characteristics, how a radio wave signal travels, fading, multipath, polarization, wavelength versus absorption, and antenna orientation. Things that a technician using a handheld radio really doesn't care that much about. But if you really want to optimize your communications so you can get the most distance, these are items you really want to know something about.
So we'd be sharing, is there a share screen that we're not seeing?
Good question. Let me try that one more time. Share. Okay, you seen it? Okay, are you seeing it now? There we go.
Yeah, there we go.
Okay. Anyway, I'll just fire up with question A01. Why do VHF signal strengths sometimes vary greatly?
Martin, I don't hear you.
Okay. Hear me now?
I think that the problem is with them because the rest of us are hearing you.
Okay. Sounds good. Sorry about that. Anyway, why do VHF signal strengths sometimes vary greatly when an antenna is moved only a few feet? So possible answers are the signal path encounters different concentrations of water vapor. VHF ionospheric propagation is very sensitive to path length. Multipath propagation cancels or reinforces signals. And all of the above are correct. Why am I not advancing? One moment here. Let me try this again. Screen share. Share. Okay. Anyway, the answer to that question is that multipath propagation cancels or reinforces signals. Over here, we have a little picture that kind of illustrates how multipath works. From a transmitting antenna to a receiving antenna, there are oftentimes several paths that radio waves can travel. and they can travel at the same time. You have a direct path, then you've got a path that's reflecting off a building, got a path that's reflecting off of the ground. And for example, these all arrive at the receiving radio at slightly different times, causing distortion or echoes. So anyway, if you have a reception that is varying greatly in signal strength, just move a few feet, and generally that will correct the problem. Question 2, A2. What is the effect of vegetation on UHF and microwave
Is your sound
signals?
up all the way?
Yeah, I gather you're still not hearing me, are you? Sorry about that. And the answer is absorption. Trees, especially pine trees with needles, can actually absorb UHF and microwave signals, not so much on the VHF band. So absorption can be a key area if you are in a forested area. A03. What antenna polarization is normally used for long distance CW and SSB contacts on the VHF and UHF bands? Well, generally, as emergency communicators, you're not going to be using CW or SSB. You're going to be using FM, but the answer is horizontal polarization, which is the opposite of what you're normally using when you're using a handheld radio that has the antenna sticking straight up. That's a vertically polarized antenna. Horizontal polarization is really best for long distance, meaning hundreds or thousands of miles communications. A04. What happens when antennas at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization? The received signal strength is reduced. Remember, you want to have the antennas that you're using for your communications, or the transmitting side and the receiving side, using the same orientation and the same polarization. So for example, if you're using handhelds, you want to make sure that the antenna is held vertically. If you hold it like a cell phone, kind of flat, and the other person has theirs of vertical, you're not going to have the optimum communication. So remember that when you're using a handheld VHF radio, you want to hold the antenna vertically. A5, when using a directional antenna, how might your station be able to communicate with a distant repeater if buildings or obstructions are blocking the direct line of sight path? Well, again, generally with a handheld radio, you're not going to be using a directional antenna. A vertical antenna on a handheld is omnidirectional. Now you can get antennas you can add to your radio set that are very, very directional. Oftentimes amateurs use those to talk to satellites, for example. But if you have an antenna like that, you can find a path that reflects a signal to the repeater. For example, in this path, you can find that are reflecting off off of as a building, you can get a much stronger signal to the receive station. A6. What is meant by the term picket fencing? This is one you sometimes experience when you're in your car operating radio. And it sounds like kind of a flutter on the receive side of the transmission. And what it is as you're driving along, the multipath varies from place to place, and that can sound like a flutter as you're driving along. A07, what weather conditions might decrease range at microwave frequencies? Generally, as a technician, you're not operating at microwave frequencies, but you do have, when you are a licensed technician, you do have authorization to operate in a couple of bands that are very near microwave frequencies. And precipitation can really affect the range at microwave frequencies. The rain is of a size, the droplet size, which can really absorb the radio waves at those very, very high frequencies. So precipitation would be the right answer to question A07. Question A08. What is a likely cause of irregular fading or signals propagated by the ionosphere? Again, as a VHF user or a UHF user, you're not really going to see much of a reflection off of the ionosphere. You're directly, it is line of sight pretty much all the time. But again, a random combination of signals arriving at the receiving station following various paths. And as the path length varies, there'll be a slight delay in time, and the signals will reinforce sometimes and sometimes cancel, and you'll have pretty dramatic fading. A09. Which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized? Again, this is not one you're going to find very often when you're using a handheld radio for VHF or UHF communications, because you're simply not going to bounce signals off of the ionosphere. But the question to this is that FM voice is not usable. And this is a reason why FM modulation is not generally used for high frequency communications, because it does not propagate very, very well. So when you're using high frequency communications, you're normally voice, you're normally using AM or single sideband. A10, what effect does multipath propagation have on data transmissions? Since data transmissions are transmissions of tones very, very fast, when you have a multipath transmission, there can be some some variations in the timing of the pulses. And since a successful digital transmission really requires really good timing between those pulses, that will cause a real issue with your transmission, and the error rates are likely to increase. And digital transmissions have an error correcting feature that detects errors and sends a signal back to the transmitting station and says, could you send this block one more time because I didn't receive it properly. So, but generally, again, with VHF and UHF transmissions, you're not going to see too much multipath since they are line of sight. A11, which region of the atmosphere can reflect or bend VHF and high frequency radio waves? And if you get into HF, you live and die by the state of the ionosphere, which is a layer in the atmosphere that has charged particles about between 200 and 400 miles up, and is the primary reason that high frequency radio waves can be reflected off of the ionosphere for very long distance communications. At the VHF and UHF frequencies, those radio waves simply pass right through the ionosphere in most cases, and are not reflected. There are certain cases where all of a sudden the ionosphere gets to a state where it can reflect those frequencies, and all of a sudden you can transmit hundreds of miles. Very uncommon, but it does happen occasionally. A12, what is the effect of fog and rain on signals in the 10 and 6 meter bands? One thing you probably may not know as students studying for your technician license is once you are licensed, you do have the authorization to use certain frequencies in the 6 and 10 meter bands, which can actually give you a fairly good long distance communications if you have the right kind of radios and antennas. But anyway, fog and rain has very little effect on those bands, which is a great thing. Over here is a little picture that shows you what frequencies you have in those bands. For example, technicians in the 10 meter band have authorization to use these frequencies in this range, and on the 6 meter band they have the authority to use transmissions in the entire band. A T3B, electromagnetic wave properties, wavelength versus frequency, nature and velocity of EF waves, relationship of wavelength and frequency, spectrum definitions for UHF, VHF, and high frequency. T3B is 01. What is the relationship between the electric and magnetic fields of an electromagnetic wave? They travel at right angles. For example, in this little graphic, this is a vertically polarized antenna, and the electric field is vertical, and the magnetic field is horizontal. If this were a horizontally polarized antenna, the field that is the electric field would be rotated on 90 degrees, and it would be horizontal. Now here's a key one. B02. What property of radio waves defines its polarization? And the answer is the orientation of the electric field. In the graphic, you have a vertically polarized antenna. The red color is the electric field of the EM wave. In the bottom graphic, you have a horizontally polarized antenna, and the electric field is the horizontal component of EM wave. And just remember, for good communications, the antennas on both ends of the transmission need to have the same polarization. If you're using a handheld radio, that's almost always you're going to want a vertical polarization. So you want to make sure you're holding your radio with the antenna straight up and down. B03. Again, what are the two components of a radio wave? As you just saw in the graphic, you have electric and magnetic fields at right angles to each other. That's why it's called electromagnetic radiation. B4, what is the velocity of a radio wave traveling through space? The speed of light. Generally, for amateur use, we just round it up to 300 million meters per second, which is within 1% of actual speed, which is 299 million meters per second. So we just round it up. Also, why that really doesn't make too much difference is that the speed of light does vary slightly depending on the medium that it's traveling through, which takes us to this calculation. If you ever want to compute what the actual speed of light is in a material, you can use this beautiful equation to determine the actual speed of light, which no one in the right mind ever does. B05, what is the relationship between wavelength and frequency? This is a key one. As you discuss radio waves, the wavelength gets shorter as the frequency increases. So for example, here is an example of a low frequency radio wave, and there's a long distance between the peaks, for example. Here's a higher frequency and there's a shorter distance. For the VHF radios that you're commonly going to use, the distance between these peaks is about 2 meters, about 6.5 feet. At the UHF frequencies that you're going to use, the 440 band, the distance between these peaks is about 70 centimeters, which is just over 2 feet. So as the frequency goes up, the wavelength decreases. As the frequency goes down, the wavelength increases. What is the formula for converting frequency to the approximate wavelength in meters? It's pretty straightforward. You divide 300 by the frequency in megahertz. For example, if you're operating in the VHF range at 144.5 megahertz, and you apply that equation, you find out that the wavelength of this frequency is 2.076 meters, which says, oh yeah, this is the 2 meter band. In addition to frequency, question B07, in addition to frequency, which of the following is used to identify amateur radio bands? And I've used this as a few times. Oftentimes, the approximate wavelength in meters is used to identify the band. Over here's a chart from the ARRL, which gives an indication of the various bands that amateurs use. The 160 meter band, where the distance between the peaks of the waves is 160 meters, which is over 400 feet, to the frequencies you would normally use as an emergency communicator, the 2 meter band and a 70 centimeter band, 134 megahertz and 420 megahertz bands. So if someone says, oh, I'm working on the 33 centimeter band, that says, oh yeah, they are actually operating .400 and 20 megahertz. They just go back and forth. So you just have to know both. Question 8, what frequency range is referred to as VHF, very high frequency? And the answer to that is 30 to 300 megahertz. In this chart, you can see the common bands used by amateurs and the frequency range used in those bands, and the most common mode that is used. Mode meaning the kind of modulation used. For HF bands, most commonly it's either a lower sideband or upper sideband, which is a kind of AM modulation. And for the higher frequency bands, It's most commonly FM, but occasionally some hams do use a single sideband, which can be either USB or lower sideband. But almost always in VHF and UHF frequency bands, it is almost always FM. And the corresponding question: what frequency range is referred to as UHF, ultra high frequency? And that's the 300 to 3000 megahertz band. The one that you use as technicians are the 70 centimeter and the 23 centimeter bands. 23 centimeters, pretty uncommon. Almost always if you're on UHF, you'll be using a 70 centimeter band, 430 to 40 megahertz. And again, what frequency range is referred to as high frequency, HF? That's from 3 to 30 megahertz. So it is the 80 meter band down to the 10 meter band. The 160 meter band is actually called low frequency or medium band sometimes, but most commonly it is called LF for low frequency band. While 80, 40, 30, 20, 18s, and so on are high frequency bands. B11B, excuse me, B11. What is the approximate velocity of a radio wave in free space? It's approximately the speed of light, which is 300 million meters per second. T3C, propagation modes, sporadic E, a meteor scatter, auroral propagation, tropospheric adducting, F, the region skip, line of sight, and radio horizon. As a VHF and UHF user, the two that are really important to you are line of sight and the radio horizon. Since the longer distance propagation are generally not used in emergency communications. They're used more by hams that are trying to see how far they can talk. So C01. Why are simplex UHF signals rarely heard beyond their radio horizon? And the reason for that is that UHF signals are usually not propagated by the ionosphere. Again, you're at A, you're transmitting, UHF is line of sight. It just goes right up through the ionosphere. While a lower frequency in the high frequency range will oftentimes bounce off the ionosphere, bounce off the ground, bounce off the ionosphere, and this could happen several times, and you can have communications over several thousand miles. But with UHF, it's line of sight. Depending upon how tall your antennas are on the transmitting side and the receiving side, you're talking several tens of miles maximum generally. But there are occasions that we'll talk about in a bit that can't increase that range. C02, what is a characteristic of high frequency communications compared with communications on VHF and higher frequencies? Again, as I just mentioned, if the conditions are right, high frequency communications can reflect off of the ionosphere and the ground, and it can communicate over several thousand miles. And that's what hams that use high frequency love to do. They love to talk to Europe. They love to talk to Asia. C03. What is a characteristic of VHF signals received by auroral backscatter? Okay, this is one you're generally not going to use on a regular basis, but you can use auroral backscatter to actually bounce your VHF signals off of the aurora borealis. And oftentimes the signal strength is distorted and it varies considerably. And you can think about that if you've seen the aurora, it kind of expands, contracts, and shimmers. And as it does that, the signal strength that is bouncing off of it does vary considerably. C04, which of the following types of propagation is most commonly associated with strong, with occasional strong?
Max, come.
Pardon? Which of the following types of propagation is most commonly associated with occasional strong signals in the 10, 6, and 2 meter bands from beyond the radio horizon? Again, it's a propagation mode that's not seen very commonly, but it's called sporadic E because at VHF frequencies, it's oftentimes possible, if the conditions are proper, to actually reflect signals off of the E band in, or the E layer in the ionosphere. Doesn't happen very often. As an emergency communicator, you're not generally going to see it, but very occasionally, all of a sudden, you may be talking and receive a signal from a couple hundred miles away, and that's because it is using a reflection off of E layer, and you're getting in very long distance communications. C05, which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations? This is one actually you will see occasionally, especially if you're operating in mountainous areas. It's a thing called knife edge diffraction, most commonly off of the tops of mountains. Here, for example, you have a line of sight transmission. Here is a transmitting antenna and a receiving antenna on the far side of a mountain. Generally, you wouldn't expect to receive the transmitted signal at this location because the mountain blocks it. But there are conditions where you can actually have the radio wave diffract off of the top of the mountain and almost kind of bends, so you have a direct path from the transmitting location across the top of the mountain to the receiving location. You can't count on that happening, but it does happen occasionally when things are just right. C06, what type of propagation is responsible for allowing over the horizon VHF and UHF communications to ranges of approximately 300 miles on a regular basis? Again, this one is really dependent on the atmosphere. It's a condition called tropospheric ducting. Occasionally, you'll have a layer of cool air close to the Earth and a layer of warm air at an altitude of 20 to 30 miles above the surface of the Earth. In that case, it's possible for a VHF signal to actually be reflected off of the Earth, off of the top of the duct, and actually you can get ranges, as I said, of several hundred miles. Again, it's not that common. It only happens a few times a year generally, but if you're on the radio and all of a sudden you get this communication from a ham that's 200 miles away on your VHF radio, that's what's happening. Tropospheric ducting. And here is another one that some hams really like to try out. What band is best suited for communications via a meteor scatter? It's kind of a specialized thing that some hams like to play with, but the 6 meter band is the best band for experimenting with this. Even though the meteor flashes are very short, you can establish communications between two widely separated locations using meteor scatter, and you actually reflect the radio signal off of the ionized gas that's generated as a meteor you're shooting through the upper atmosphere. There are hams that actually special atmosphere. Again, you have a cool air layer with warm air layer over it. And occasionally you can reflect your VHF signal for several hundred miles using tropospheric ducting. C09. What is generally the best time for long distance 10 meter band propagation via the F region? And from dawn to shortly after sunset during periods of high sunspot activity. And what happens is during late hours of high sunspot activity, the sun causes the F layer in the ionosphere to split into a couple of different layers, and that enhances long distance communications. Again, as a as a technician doing emergency communications, this is not a propagation method you're ever going to utilize, but as an amateur experimenting to see how far you can talk, it works out pretty well sometimes. C10, which of which of the following bands may provide long distance communications via the ionosphere's F region during the peaks of sunset of sunspot cycle? And again, like the previous question, it's reflecting off of F layer of the ionosphere, and it's best on 6 and 10 meters. That's the frequency that actually refracts best off of those layers. 11. Why is the radio horizon for VHF and UHF signals more distant than the actual visual horizon? We talk about line of sight. You can actually communicate on VHF and UHF slightly further than the actual line of sight you can see. That's because that the atmosphere actually refracts radio waves slightly. In this example, you have the curve of the real Earth with a couple of antennas. And if you experiment, you can see the actual distance you can transmit is slightly more than the actual distance based on the height of the antennas. This is an effect called the 4/3 Earth radius effect, and it's used mostly in microwave communications, where the actual line of sight might only be 40 miles, but because of the 4/3 Earth radius effect, you can actually get out to about 60 miles. Which takes us to the end of the question pool. So anybody have any questions? Things if they want amplified? Okay, I'm not hearing anything. So
Hey, Marty, either they all get it really well or they don't get it at all. So I'm not
Yeah.
sure what to say.
okay, hopefully they all got it really well. They have been studying their books. They've been taking the sample questions and have it wired. So Steve, I'll take it back to you.
Thank you. Ray, could you turn the recording off, please?